Hello everyone. So far we have seen three methods of rotation representation, which is rotation matrix, axis angle representation, and Euler angles. And we have also seen some relevant MATLAB commands for them in my video. At the end of my video for axis angle, I went through some of them and showed you. So now we are going to look at the fourth and the last method of representing orientation, which is called unit quaternions. And unit quaternions are basically the hardest to imagine, the hardest to understand, right? Because they are not something you can easily imagine in 3D. Like Euler angles are three rotations. Axis angle is one rotation about the specific axis. Rotation matrix you can understanding by those dot products. But when it comes to quaternions are hyper-complex numbers. And by hyper-complex, I mean instead of having one real part and one imaginary part, they have one real part, but they have what? They have three imaginary parts. Okay, so their imaginary parts have they have three axes of imaginary parts and one axis of real. So they are like complex number, but instead of two axes, they have four axes. And since we cannot really imagine anything beyond 3D, for this 4D vector, there is nothing that we can physically use to imagine them, okay? And that makes it, for some people, hard to digest, this method. And plus they have one redundancy. Clearly you can see that there are four parameters, q0, q1, 2, and 3. And so there is one redundancy. So what makes them any good if they have a redundancy, if they have they are hard to understand? What's good about them? I'll show you. The good thing about them is mathematically they don't have singularities, right? So Euler angles had singularities and axis angle had singularity. And here I can show you this method does not have a singularity. That's the best thing about this method, which makes it one of the reliable techniques when you're trying to solve like inverse orientation problems or so. They typically use quaternions for that to avoid mathematical singularities. So let's take a look at that. As I said, they are hyper-complex numbers. So there is a real part we call q0, and there are three portions, three parts of the imaginary part, q1i plus q2j and q3k. And here I, j, and k are different from the unit axes along x and y and z axes. They are bases of the complex number. So I squared is -1, j squared is -1, and k squared is -1. So j and k are basically the same as I of the complex numbers. And if you multiply all three of them, also you would get a 1. So this is a different definition. Okay, this we never had. So far, I squared, j squared, k squared equal to -1. You can understand it's like generalizing I to also j and k. But this part that the three of them multiplied together is also -1. That's something interesting, okay? And it might kind of come from the fact that if you square this guy, this ijk, when you square it, it is like I squared, j squared, and k squared, correct? And you know that I squared is -1, j squared is -1, k squared is -1. Correct? So from here, you see that this ijk, the whole thing squared, is also -1. Right? And that really does not make too much of sense based on what we have here, that the entity itself is -1. Well, if the entity itself is -1, then when you square it, you're going to get +1, not -1, right? So this is an additional definition that does not match the rest of it. Okay, so this is another definition. Again, I'm emphasizing that the way that these ijk are defined, they are defined such that the product of the three is also -1. And again, this does not come from these other things that the other square terms are -1. Okay, it does not come from that, because you clearly see it does contradict that. So this is an extra condition that you apply to I, j, and k. And so this is for the square terms and when everything is multiplied together. Now you might say, fine, now what if when they are multiplied together, like I times j, they're kind of similar here to the cross products of the unit vectors ijk. Again, these ijk are different than unit vectors ijk. But if you remember, for example, I cross j was k, correct? And then j cross k was I, and then k cross I was j. So these are kind of like those cross products that we had in unit vectors, but here there is no cross and there is no unit vector. These are just the base of complex numbers. And so if you reverse the order, just like the cross product that I cross j was k, j cross I was -k, that's the same thing here. J times I is -k, k times j is -I, and then k times I is negative. I times k is -j. Okay, so again, these complex bases I, j, and k, they follow all of these rules. Okay, this is what mathematicians defined to make this hyper complex number set work. And you see, they are not like perfectly like a generalized version of complex numbers. Then another way that you can show this quaternion is you show it as a couple of eta and zeta, where eta is the real part of it, and zeta here is the imaginary part of it, but it is a vector. That's why you see here I used bold font. Okay, so zeta is a vector. It has three components, q1, q2, q3, and eta is the real part of it, which is q naught. So if you see, they show it also with eta and zeta. That's the same thing, just squeezing the three complex part into a complex vector zeta. Okay, so these are just some of the notations and some of the principles when they define these hypercomplex number unit quaternion. That's what they had to define to make it work. And the first thing is, what's the magnitude of this complex number? Well, it's just similar to the other complex numbers. The magnitude of a complex number is what? The real part of the square plus the imaginary part of the square. Now here you have three parts of imaginary, so you have to square all of them, add them all to the real parts squared, take the square root of that. So this is going to be what? The norm or the magnitude of the unit quaternion. And this has to be equal to what? 1. Okay, this square root has to be equal to 1. That's why we call them unit quaternion. If it's not 1, then they're just a regular quaternion. And that's what makes this redundancy justifiable. Remember, I said there are 4 parameters. One of them is redundant. When there is a redundancy, there is always a what? A constraint, right? So my constraint is that this relation exists between the 4 of them and 1. So basically, if you know 3 of them, the 4th one can be determined from this magnitude of 1. Okay, so that's where this redundancy is coming from. Okay, clear? Good. Now that we know about their magnitude and how we write them and their basic principles, what if you multiply a scalar, a single real number, by a quaternion? So all you need is just like real numbers, right? When we multiply 2 by like 3 plus 4j, we multiply this 2 by each one of them. So 2 times 3 was 6, 2 times 4 was 8i. The same thing here. When I multiply alpha by q, I multiply alpha by all of the 4 components from q naught to q3. No big deal. Also, again, similar to the complex number, we have a conjugate. And also here you will call it inverse, and we'll talk later about it. But what's the conjugate? Conjugate, remember, for the complex number like 3 plus 4i, it was what? When we applied the conjugate to it, the real part stayed the same, but the imaginary part was negated, like this. The same here. When I do a complex conjugate, and for conjugate of quaternions, I'm not going to use bar, I'm going to use star. So complex conjugate of q is what? The eta stays the same, but the zeta, which is the imaginary part, is what? Is negated. So it's going to be q naught plus minus q naught minus q1i minus q2j minus q3k, okay? That is the conjugate of a unit quaternion. So far we learned about multiplying them by a scalar, how to do conjugates. Now also addition and subtraction is very easy, right? So I haven't written it here, but you know clearly if I want to add two quaternions together, so I have one q, which has q naught all the way to q3, and then another one, you might call it W, which has W naught all the way to W3 times K. When I add them, I add the corresponding elements together, correct? So if you want, I can add it for you here, but it's not such a big thing. But, well, let's just do that for the sake of completeness of this lecture. So addition and subtraction is if you want to add something like this. Okay, and then plus or minus something again like that is equal to. So first thing first, let me make all of this black, the same color, good. So these are all q's, and let's say here instead of q I use w, correct? And I am simply adding or subtracting these quaternions together, so it is going to be basically q naught, and then basically plus or minus w naught, correct? The real part of it, and then plus I times q1, and then again plus and minus w1, right? Plus again j times q2 plus and minus w2, and finally plus k times q3 plus and minus what? w3, and that's it. Okay, so maybe this one I can bring it to the bottom equation and make it all black and expand it a little bit. There we go. Okay, so if you want to add or subtract, it's very basic. So far, all good. Now you might say, what about when I want to multiply them together? Okay, what's the product of them? So let's talk about that. Okay, so here it says that the product of two quaternions is if one of them has a real part of eta 1 and imaginary vector of zeta 1, the same thing for eta 2 and zeta 2. When you do it, basically, you'll end up with another quaternion where the real part of the product quaternion is what? The product of the two real parts minus the dot product. Here the symbol actually stands for a projection or dot product, or the dot product. So instead of this, if you want, you can say zeta 1 dot zeta 2. The thing is, dot, you really define it for vectors really, but this is basically similar to, as I said, zeta 1 dot zeta 2, okay? And the imaginary part of it is what? The real part of the first one times imaginary part of the second, plus the real part of the second one times imaginary of the first one, plus the cross product of the two imaginary parts, okay? So let's practice on it a little bit and see where this formula comes from. And then we can also do the product of quaternions using a matrix notation and matrix format. But first, let's work on this formula, see where this one comes from, and practice on it a little bit. And then we'll go from there. So here, this is what I have. Now, where does it come from? So what I have here is I have Q naught plus Q1 I plus Q2J plus Q3K, the whole thing times. And for the second one, as I said, let me use W. So I will use W naught plus W1 times I plus W2 times J plus W3 times K. So you clearly see why people show eta and zeta instead of all Q's or all W's, because it's shorter, right? Instead of 9 letters and a bunch of pluses, correct? You just show them with a simple couple like that. But I want to expand it and show where it comes from. So if I do it here, I have 4 terms, and 4 terms, you will end up with 16 terms. So there's going to be Q naught times W naught plus Q naught times W1I, Q naught W times J, Q naught W3 times K, plus. Then I go with Q1, so there's going to be Q1 W naught I plus Q1 W1 I squared plus Q1 W2 IJ plus Q1 W3 IK. Plus, now we go with Q2. So there's going to be Q2 W naught J, Q2 W1 JI, plus this Q2. Q2 W2 J squared, plus Q2 W3 JK. And finally, Q3 W naught K, and then Q3 W1 KI, Q3 W2 KJ, and Q3 W3 K squared. Okay, so if I expand it, I will get 16 terms, and now my goal is to use the rules I had for quaternions, simplify this, and see where this one comes from. And the rules that I had are these guys that you can see here. I squared, J squared, K squared, I, J, K, they're all -1, and then the product of them that has an order. Okay, so for the sake of reference, I just put them here for you, so we can see them together, and you can see where they are coming from. Okay, so let me bring them even a little bit closer. Good. So let's start. The first row is all good. Start with here. I squared is -1, J squared is -1, K squared is -1. Then we have what? I times J is K. J times I is -K. I times k, if you look at it, is here. That is negative j. If you have k times I, which is here, that's positive j. And finally, I have j times k, which is what? That's I, as you can see. And then what? K times j, which is negative I. And that's it. Everything else is simplified. So now, if I go back and try to rearrange this, what do I get? So it is going to be, there is a portion of the terms that they do not have any I, j, or k. And this includes this one, this guy, this one, and this one, the diagonal terms. So it is q naught w naught plus what? q1 w1 plus q2 w2 plus q3 w3. This is the term with no I or j or k. Then there are some terms that have I in them. What are those? It's this guy, it's this one, it's this one, and it is this one. Correct? So let's write them down. So it is going to be q naught w1, and then plus q1 w naught, and then plus q2 w3, and minus q3 w2. Correct? So these are my I terms. Then I go for my j terms. For j terms, I have this guy here. I have this one here. I have this one here. And I have this one here. So plus q naught w2 minus q1 w3 plus q2 w naught and plus q3 w1. And finally, we have the last terms of k, which is basically whatever has remained. And if you look at them, it is q3 w, q naught w3, and then plus q1 w2 minus q2 w1 and plus q3 w naught. So this is going to be the result. Good. Now let's take a look at the real part first. What is this guy? So this is clearly, since you know, q naught means what? Means eta 1, and w naught means eta 2. So this guy is eta 1 times eta 2. Okay, so that is obvious. What is the next term here, this guy? q1 qw1 plus q2 w2 plus q3 w3. It looks like it's what? It's the dot product of this vector with this one, where this vector is called zeta 1 and that vector is called what? Zeta 2. So this is clearly plus what? This is clearly plus the dot product. Now, is that plus or minus? That's the thing we have to pay attention to. Because here you do not really have a dot product, okay? It's not a real dot product, it's just the product. Okay, so, but the way you define it is what? So let me explain that here. So when I have a vector like this, zeta 1 is Q1I plus Q2J plus Q3K. And then I have another one, zeta 2 is equal to W1I plus W2J plus W3K. If they were vectors, when I said really zeta 1 dot zeta 2, yes, then it would be Q1 times W1 I dot I. And you know, if they were unit vectors I, j, k, then I dot I was 1, j dot j was 1, k dot k was 1, so you will get what? Q1 W1 plus Q2 W2 plus Q3 W3. But here, it's not an actual dot product. What you do when you do this, still like you are doing element by element, but the whole element, so you will get Q1 W1 I squared plus Q2 W2 J squared plus Q3 W3 K squared. And you know that I squared, J squared, and K squared, they're all what? -1. So that's why this kind of dot product really is what? Is negative Q1 W1, negative Q2 W2, negative Q3 W3. Okay, that's why. So here, when you have this positive, that's negative of the negative. Instead of this positive, you can say negative of the negatives. So it is going to be negative of, and then all of those negatives will be what? Will be this guy. Zeta 1 and zeta 2, okay? It's not, it is kind of like a dot product, but it is for these guys where I times I is going to be -1. It's not like I dot I, where I was unit vector, which was 1, okay? So it's a little bit different. So you have to know about this definition of the zeta 1, zeta 2. And now let's look at the rest of the terms. The rest of the terms, if you look at them, there is 2 categories in each one. One category has Q naught in it, 2 terms, 1 term of Q naught and 1 term of W naught, like this. The similar thing in the other one. It's this guy and this one. It's this guy and this one. So there are terms in them that involves Q naught and W naught. If you factor them out, what will you get? So you will get, and what you can do is, in the ones that have Q naught, you can factor out Q naught. So it is going to be Q naught times what? Times W1I plus what? W2J plus W3K. If you factor out the W naughts, it's going to be plus W naught times Q1I plus Q2J plus Q3K. Okay, so these are those terms. And then on the other hand, you have some terms here that they have other Q's and W's, and one of them is positive, one of them is negative, like these guys. And what are these? Well, if you do cross product of zeta 1 and zeta 2, so when you said zeta 1 cross zeta 2, what does it mean? What's the meaning of this? It means it's a 3 by 3 determinant The first row are ijk, and ijk are these base of complex numbers, not unit vectors. We are not doing any unit vectors. The first row goes the numbers of zeta 1, which are q1, q2, q3. The next one is going to be w1, w2, and w3. And if you know, if you do it with a Sarus's law, it is going to be I times q2w3, and then minus q3w2 plus j times, if you look, it is q3w1 minus q1w3, and finally plus k times, it is going to be q1w2 minus q2w1. And if you look at these terms, they are exactly what you have here. These purple terms, if you sum them together, that's exactly zeta 1 cross zeta 2. So you can say this is what? Plus zeta 1 cross zeta 2. And what are these now? Clearly, this is your eta 1, this is your eta 2, this is multiplied as a scalar times vector zeta 2, and this is multiplied as a scalar by what? Zeta 1. So now the formula is very clear, right? The real part is the multiplication of the real parts minus the dot product of the imaginary parts, as you can see here. And the imaginary part is the real part of the first one, scalar product by the imaginary of the second, plus real part of the second, scalar product by the imaginary of the first one, plus the cross product of the two imaginary parts, which you can clearly see here. Okay, so it's quite clear where that formula comes from, and I guess that was a good practice of us first defining these, and the dot product here, the cross product here, and practicing with these important rules of IJK. Okay, so again here I specify that this is not like a perfect dot product, because here you are not doing I dot I, because I is not even a vector to do dot product, but we call it the dot product. So dot product for complex numbers, it acts similarly, but the result, you're going to get negatives here. But with that negative canceling, you're going to get the positive terms. Okay, so that's the product of two quaternions, which could be quite complicated, right? If I have four numbers here, four numbers there, even if I follow this formula, it's not the simplest thing in the world. Another way that you can do it, which is quite easier, is you can do it using the matrix format. So what you do is, when you multiply the two quaternions, QA and QB, the second one, QB, you just write it as a 4x1 vector with the real part all the way to the last imaginary part. For the first one, you convert it into a matrix. You convert it into a matrix. And the way that you form that matrix 4x4, it has some rule, okay? So the way you do it is this. This 4x4 matrix that is formed by QA has the real part of the QA on the diagonal. The real part goes all on the diagonal. Okay? Then the rest of the first row is just like as if you put the whole QA on the first row. You have, after QA naught, you have QA1, you have QA2, and you have QA3. The same thing for column 1. After Q naught, you have QA1, QA2, and QA3. So if you see, the first row and the first column are exactly as if you put QA horizontally or you put it vertically, with one difference. When you put it on the row, all of the imaginary parts are going to form what for you? A negative. So they are like conjugate. Okay, so this first row is like the conjugate of QA. The first column is like actual QA. Good? And all of the diagonals are simply what? QA naught. Now, what about the rest of the elements? Okay, you know, this is a square matrix. So now if you look at the mirror element, you're going to find the rest of them. So this is negative QA2. If you look at the mirror element of this, it is this guy. You see they have a negative sign of each other. If you look at these two, they have a negative sign of each other. If you look at these two, they have a negative sign of each other. The same thing applies for the rest of the elements. If you see these two that are mirror image, they are negative of each other. These two are negative of each other. And finally, these two are negative of each other. Okay, so it is like a skew-symmetric matrix. Okay, not like, it is a skew-symmetric matrix. With the difference that on a skew-symmetric matrix, the diagonals are all zero. Here, there is no necessity for them to be zero. They are the real part of the quaternion. That's why we call it similar to, it's not perfectly a skew-symmetric. Now, let's look at the sign of these remaining terms here, and then you can easily figure out the rest of it. It's not such a big thing. So look here. If you look at this second row, I know I have to have QA here, and I have to have QA not here, QA1 and QA not. So the two remainings for it have to be what? Q2 and Q3. Similarly here, since I have Q not here and Q2 here, the remainings have to be 3 and 1. And similarly, I have 3 and not here, so I have to have 1 and 2 here. So you clearly know that the 2 and 3, 1 and 3, 1 and 2 should squeeze in. But where do they go exactly? So let's focus on the second row. I know that the 3 and 2 has to go there. Fine. And which one is going to go there? Is 2 going to go there or 3? The problem is if 2 goes here and 3 goes here, so if I just exchange them, what happens is in this column, you're going to have 2 QA2s right below each other, and in this one, 2 Q3s below each other. And that's not how this matrix is. In this matrix, if you look, in each column or each row, you have all 4 of them. Any column, any row that you look, you have all 4 components in it. Okay, you have all 4 components in it. It doesn't matter which column or which row. You always have all 4 components in it. So the only way that here the 3 and 2 goes is to 3 come here, 2 goes there. And so once these 2 are fixed, since it is a mirror version, so if this is 3, then that is going to be 3. If this is 2, then this is going to be 2. And of course, the remaining here, these 2 positions have to be 1, and so it's 1 and 1. Okay, so the locations are clear. What goes where? The only thing remaining is the sign. Okay, what about the sign of these remaining terms? Which, as I said, are these guys. So Q3 and Q2 are good. What about the signs? Now, if you look at the signs, also there is one other thing that could be quite interesting to you. In each row, from the second row all the way to the last row, not the first one, but second to the last, there is only one negative element in each row. There is only one. So between this Q3A and Q2A, one of them has to be negative because these 2 are already positive. And which one goes there? Okay, that's another thing that you have to look. And there is another rule here also. If you look at the second column all the way to the third column, if you look at them, in each column there are two negative elements. But as I said, in each row there is only one negative element. So this is one negative in each of them. Here, these guys, they all have what? Two negative elements. Okay, and to make that happen, definitely here the QA3 has to get the negative, so this guy gets both of the two, and this one, since these two already have it, this has to be positive. Okay, that's too many rules to follow, so if you want to remember this, but you don't have to really. Engineering is not just about memorizing tons of things. It's about understanding where the tools are and how to use them. But it's always good if you can remember this quite hard thing. Okay, how to form a 4x4 matrix out of this 4x1 quaternion and then multiply it by quaternion of the second one. That will give you the same result. Okay, and so to practice that, let's just work on some numbers and see if these formulas work properly. So here I go with two quaternions, quaternion Q and quaternion W. Quaternion Q is like 1 minus I plus 2j and minus 3k. And quaternion W, and there is one problem here. The problem is it's not unit quaternion, okay? It's just a regular quaternion. It's just not a unit quaternion. You clearly see if I square these numbers and add them together, the square root of that is not 1. So this is not a what? A unit quaternion. For the product, you don't, when you want to follow these rules, you do not need the quaternion to be unit quaternion. You can use it. It's other places that it better be a quaternion like here, a unit quaternion like here, and I'll explain. So if it's just for the sake of practice, it does not really matter here that it is a unit. If you want, I can make it a unit quaternion. I can divide this whole thing by the square root of the number, and here the number is 15, right? Which is not really a square root of 15 is not really the best number. So I can modify it if I want to a little bit. And let's say here, let me do some modification. Let me make it just for the sake of knowledge. So I eliminate the I here. Let's say I don't want an I. And I make this guy also a 2. So it is 1 plus 2j minus 2k. Clearly the magnitude is 9 square root of it, which is 3. So if I just divide them by a 3, now clearly this is a unit quaternion. Okay, so that's a unit quaternion, right? Let's work with, now that we are talking about unit quaternion, let's work with them as well. And for W, I'm going to use another one. And for this one, I will go with, let's say, 2, and then minus I, and then let's say plus J. Okay, now the magnitude here is 4, 5, 6. So that's not, again, a good number. And unless I make this like negative 2, then again the magnitude is 9. So if now I divide by 1/3, I am going to get a unit quaternion, correct? So clearly here I have two unit quaternions. Now first I multiply them using the first formula, and then I apply the matrix notation and see what I get. So in this case, this is your eta 1, correct? This thing is your zeta 1, this is your eta 2, and this is your zeta 2. So if you remember, it said that Q1 and times W1 is what? Or Q times W, it is what? It is equal to. The real part of it is eta 1, eta 2, if you remember, minus the dot product. And the imaginary part of it is eta 1 zeta 2 plus eta 2 zeta 1, and then plus zeta 1 cross zeta 2. So let's apply it. So if we apply it, what do we get? Well, eta 1, eta 2 is clear, is 2 over 9. If you do dot product of them, you have to multiply each component by the corresponding version of it, and then basically negate them. So I'm looking into this guy and this one. So here there is no I, so this I will be multiplied by no I, so it goes away. There is also no k for the bottom one, so the k and k would go away. So all you have is 2 over 3j times negative 2 over 3j. When you multiply them, you are going to get negative 4 over 9j squared. And remember, j squared is negative 1. So the result of this is going to be 4 over 9. So hopefully you see what I'm doing. Now, eta 1, zeta 2. So multiply 1/3 by these two guys. If you multiply those two guys by 1/3, you are going to negative I over 9, and then negative 2j over 9. Let's do the same thing for here. Multiply 2/3 by those two guys. You will get 4 over 9j and minus 4 over 9k. And finally, for this, you have to do that determinant of I, j, and k. The first row goes the components of the first imaginary. There is no I, so I is 0. The j is 2/3. The k is negative 2/3. And then here the I is negative 1/3. The j is negative 2/3. And the k is 0. Okay, so this is what you have to do. And if we do it and we use the Sarus's method, this is going to be 0, that is 0. You are going here to get a 2 over 9j minus 2 over 9, but that's another minus, so plus 2 over 9k. And then minus 4 over 9i. That's it. Okay, and this guy goes here. Okay, so if you simplify, the result is going to be what? The result is going to be, see if my pen writes, there we go. The real part is 2 over 9 minus 4 over 9, so it's negative 2 over 9. That's the real part, and then the imaginary part is now what? Here you have negative I over 9, and here you have negative 4i over 9. You add them together, you are going to get negative 5i over 9. Here there is a j term, negative 2 over 9, 4 over 9, that's positive 2 over 9, plus another 2 over 9 is 4 over 9. And then you do the k's, that's a negative 4 over 9, that's a 2 over 9, so it's going to be negative 2 over 9. Okay. Okay, so that's your quaternion. Negative 2 over 9, negative 5 over 9, 4 over 9, and negative 2 over 9. These are the 4 numbers of your result, correct? We did it using the first formula. Now the second method says form the 4x4 matrix of QA and then multiply it by the quaternion of QB. For QB, you directly type in the numbers. So 2/3, -1/3, -2/3, and 0. You know, there is no K for the last one, for the second one. For the first one, if you remember, all of the diagonals are first the real part of the guy, which, if you look, the real part of it is 1/3. So this 1/3 okay, my pen starts not cooperating complete. Let me finish this video. 1/3, 1/3, 1/3, and 1/3. Okay, this is for what? This is for the diagonals. Then, as I said, the first column is just putting the whole QA on. So whatever it is, which is 2/3, there is 0i, so 0, 2/3, -2/3, right? 0, 0i, 2/3j, and -2/3k. Just directly plug it into the first column. For the first row, though, you have to do what? You have to negate all of these imaginary parts. So it's negative of 0 is 0, negative of 2/3, and negative of -2/3, which is positive 2/3. So this portion of it is no hard. Okay. Now here, since I put the I component and the constant component, these two guys have to be the J and the K. Which one is which? All you need is to just remember two of them, even if you don't remember the whole thing. If you just go back and remember just two of the terms, where they go, this is negative of the last one, this is positive of the first one, and this is negative of the first one. So if you just know these three, the other three will be mirror image of them will be negative of them. So if you just remember this corner, this triangle, it's over, right? So negative Q3, Q2, negative Q1, that's all it is, right? Negative Q3, positive Q2, negative Q1. So negative Q3, so negative of -2/3 is positive 2/3. See if I can move that out of the way. This is positive Q2, and Q2 is positive 2/3 also. And this is negative of Q1, and there is no Q1, so that's 0. Okay, so now that we got these guys, the rest of it is basically the mirror image with respect to the main diagonal, right? So if you remember, this was your main diagonal. And so here, if you mirror this 2/3 with respect to diagonal, this element is also going to be 2/3, but with a negative sign. Remember, when you mirror any element with respect to the main diagonal, it should be negative of that. So this is going to be negative 2/3, this 2/3, right? And this 0, negative of that is also 0. That 2/3 is going to be negative 2/3 here. So that is the matrix for Q of A. This is the quaternion for Q of B. And if you multiply, the result should be a 4x1. And if you do that now, you clearly can see here it's going to be 2/3 and then 2/9. I'm sorry, 2/9. And then let's just make sure everything is exactly right. That's as far as I can see. Good. So always double check it before you carry out any other thing. Make sure that you have done it all right. So these I did right, this I did right. Negative Q3, Q2, negative Q1. Negative Q3. That's right, Q2. Negative Q1. That's perfectly correct. This is perfectly correct. And also let me double check this top results here. So 2/9, that's perfectly right. When I do the product of these two, it is going to be this one times this one. But you know, there is no I, there is no K, so the result is simply JJ. So it is negative of the products of the elements, which is 4/9. 2/9 minus 4/9, that's negative 2/9. So it looks correct to me. So now if I do the product of matrices, it's 2/9. That's plus 4/9. It's going to be 6/9. So this one does not match right off the bat. The next one is negative 1/9 minus 4/9. That's negative 3/9. This one also does not match. When you go in next one, you get positive 4, positive 2, that's positive 6, minus 2, that's 4. That's the only one that is matching so far. And K is negative 4, positive 2, that's negative 2. Okay, so the J and the K do match. The I does not, and the constant is not. So I'm going to double check them right now. Okay, I found where the sources of error were. So here, this element 2 of the result is negative 5/9. I made a mistake. So if you multiply the second row by the vector, you're going to get negative 1/9, and then you're going to get negative 4/9. So it's going to be negative 5/9, which also matches this guy. So clearly you see I, J, K matching perfectly. Now, and I found that here was the source of mistake. This is actually 6/9, and this should be plus this. And the reason is when you multiply this together, the real portion that comes out is 1/3 times 2/3, then plus 2/3j times negative 2/3j. Because the rest of them, you're not going to get any constant number out of it, right? Because there is no I, or there is no KK, you only get JJ. And here, this is going to be negative 4/9 j squared, but j squared is negative 1, so you're going to get 2/9 plus 4/9. And that should be 6/9. So this guy is actually 6/9. And so now they perfectly match. Okay, so both of those formulas are correct. And in one of them, you can do the product using a matrix multiplication. In the other one, you have to go through a cross product, dot product, vector scalar, and scalar scalar. I prefer this one. This is a lot easier. Plus, in many robotics applications that we do everything based on matrices, and especially rotation matrices, it's a good idea to also turn this into a matrix. Okay, so now we have learned a lot about quaternions, their magnitude, scalar product, conjugate, addition and subtraction, product of them in different versions. Now there are a couple of things that we have to talk about. One of them is inverse. Okay, in here I said that the inverse is the same as the conjugate, but that's only true for a unit quaternion. In general, when you talk about the inverse of a quaternion, it is equal to its conjugate over the magnitude of it squared. Okay? So it is like a q naught minus q1i minus q2j minus q3k divided by q1 squared, or q naught squared plus q1 squared plus q2 squared plus q3 squared. So this is the definition of the inverse of a quaternion in general. In general, this is the definition of inverse of a quaternion, which is not unit quaternion. In our case, we are only dealing with unit quaternions, and for a unit quaternion, this whole thing is a 1. So you clearly see that the conjugate becomes what? The same as the inverse. Okay, because the magnitude is 1. So the fact that you see here, I said the inverse and the conjugate are the same. This is true if and only if it is a unit quaternion. Okay, but the definition of inverse, you clearly see it is a little bit different than simply conjugate. And maybe I add that somewhere here for you. And I say in general, for a quaternion that is not, that does not have, let me add it under this line 3, okay, because we want our lecture to be complete, and I don't make this item 4, that does not have a magnitude of 1, we have, and here we can define our inverse to be the quaternion, the conjugate divided by, and then what we have is the norm squared. Okay, so you're going to have the norm, then you're going to square it. Okay, so this is the general definition of inverse. Okay, so we talked about all of that. One terminology here, this, as I said, when you put this QA here into this matrix format to use it for multiplication, this format of the quaternion, it's called the matrix format of the quaternion. So you can always show quaternions as also what? As a 4x4 matrix for different applications. Okay, so this is the matrix version of QA. Now, we here so far we just talked about the arithmetic and the basics of quaternions. Now, what do they have to do with the rotations, right? That's the main goal, to use them for rotations. So the Hamilton's rotation formula or theorem says that if you have vector r and you want to rotate it by a unit quaternion to get vector r prime, then the rotation matrix that you need here, the 3x3 rotation matrix, to multiply by r and get you r prime. Again, if you look here, I'm multiplying it by the old vector to get the new vector. So this rotation matrix is very similar to the axis angle. It doesn't take you from new frame back to old frame. Okay, it takes you from, by pre-multiplying it, it takes you from old to the rotated, which is the new. Now it says the rotation matrix for the quaternion is basically this rotation here, this matrix here. Okay, so the rotation matrix for a quaternion is like that. And so if we just plug in the values of Q0 to Q3, it gives me a 3 by 3 matrix, and I can multiply it by any vector to rotate it. Okay, so for example, let's go ahead and take a look at MATLAB. So I'll show you through my next two formulas that you can relate your axis angle representation to quaternions by these two formulas, and I'm going to show you. Okay, so the real part of the quaternion is cosine of the half angle of rotation, and the imaginary part of it is the axis of the rotation, k unit axis times sine of half angle. Okay, as I said, I'm going to prove this right now and we are going to use them. But let's say here all I want is a simple rotation about the z-axis with 90-degree angle. So my quaternion q is going to be what? It is going to be cosine of half of the angle, and then k, which in this case is what? 0, 0, 1 times sine of the half angle. Okay, so this is my zeta, this is my eta based on these formulas. So that quaternion I'm getting should represent a rotation of 90 degrees about the z-axis, okay? And here is that quaternion. Now the question is, how do I know this quaternion is right? Well, if I get a rotation matrix for this quaternion based on this formula that I just showed you, it should give me a rotation of what? Z with angle 90 degrees, correct? If it gives me a rotation Z of 90 degrees, then it means this formula is working, correct? So what I'll do is either I can plug in these numbers as Q0, Q1, Q2, and Q3 right into this matrix and calculate it manually, or I can use the built-in MATLAB command called quat to rotation matrix. I just pass to it Q and it gives me the rotation matrix, and all it does is just that plug. Now, does this look like a rotation Z matrix to you? Absolutely. If you look at the last row and the last column, you clearly see this is a rotation Z matrix. This is cosine of theta, cosine of 90, you know it's 0. This is negative sine theta, negative sine of 90 is negative 1. This is sine theta 1, and this is 0. So this is perfectly a what? A rotation about z-axis with angle 90 degrees. You see, that's perfectly correct. Yes? It's working absolutely right. And I can try another example for you. So let's say I want to go with a 60-degree angle. Okay, again, about z-axis, but 60 degrees. So this is my quaternion, and now if I pass it to, gives me this rotation matrix. Now, does this rotation matrix look like R of z and 60? Yes, because this is what? If you look at this guy, what is that? Yes, that is what? Cosine of 60 degrees, which is 1/2. This is negative of sine of 60 degrees, and sine of 60 degrees is square root 3 over 2, which is 0.866. Then sine of 60, and then what? Cosine of 60. So you see perfectly it is working. So, and these are exactly coming from these numbers, okay? They're not such a big deal. So when, as I said, I use my theta of 90 degrees and I use my k to be 0, 0, 1, it means that, as you saw, my quaternion is going to be 1 over square root 2, 0, 0, 1 over square root 2. Okay, based on these two formulas, which I'm going to prove to you. Now, if I plug my numbers here, you clearly see what's going to happen. So anywhere I have Q1 and Q2, clearly they are 0. Okay, all of these terms are 0 because they're all Q1 and Q2, which are 0. And then Q0 and Q3 are what? They are both 1 over square root 2. So here I'm subtracting the square of Q0 and Q3, but they are the same thing. So the result of this thing is 0. Here I'm multiplying them together. Anytime you multiply these two numbers, you're going to get the 1/2. Negative 2 times 1/2, the whole thing is going to be negative 1. This is, of course, 0. Again, here you're multiplying, that's 1/2 times 2, this is 1. Here you're subtracting, so you're going to go down to 0. This is 0, this is 0, this is 0. And here you're adding the square of them. The square of them is 1/2, 1/2 plus 1/2 is 1. So if you clearly see that, this is going to be turned out to 0, 1, 0. Negative 1, 0, 0, 0, 0, 1. Right? That's the rotation matrix I get from this formula. And if you look, this is exactly the previous rotation matrix that I had. Okay? So my rotation matrix is working perfectly. Okay? It is working. Now, another way I can check it is, if I multiply that rotation of z at 90 degrees by a vector r, is that going to give me vector r prime with a meaningful thing? Well, let's find out. So here, I'm going to go back to my Q. I'm going to get my rotation matrix for that, correct? Which is this guy. And then this is the rotation matrix. If I multiply that by some sample vector, let's say 3, 0, and 0. But of course, it has to be a column vector. If I multiply that, the result is 0, 3, 0. Now, does that make sense? Of course. Why? Because what I did is, this is my coordinate frame. And here I just show it from the top. So this is x, this is y, this is z. The vector I chose was 3, 0, 0, so it was this vector. And then I rotated it 90 degrees about z. Correct? So it brings this green vector right onto what? This black vector. Which is clearly what? 0, 3, 0. And so you see, my formula is also working perfectly with this rotation matrix. Okay, so now it is, I guess, clear. Whenever I give you a quaternion, you plug the numbers Q0 to Q3 all into this rotation matrix. It gives you a 3 by 3 rotation matrix. And if you pre-multiply it by any vector, it is going to rotate it for you. Okay, so now you can clearly see the relation between what? Quaternions and the rotations, okay? Or a rotation matrix. Good, so that is clear, that's good, very nice. Now here I use the formula, which was the relation between the axis angle and the quaternions. Where does that come from? Okay, let's first go and take a look at this, and then we go to the next step of the inverse orientation problem. And if I give you a rotation matrix arbitrary, could you give me the Q0 to Q3 that makes such rotation matrix happen? So remember, we had this command here. What command was it? The command was quat to rotation matrix. That is using exactly this formula. It takes the Q0, 1, 2, 3, plug it here, it gives you the rotation matrix. What I'm gonna do down here is what? I give you the rotation matrix with entries R1, R1, 2, all the way to R3, 3. I want you to give me the Q's back. So this is gonna be the command what? Rot M to quat that you have in MATLAB. What is this one? Here it takes K and theta and it gives you the quaternion. So this is the command what? In MATLAB is called axis angle to quat. There is a command like that in MATLAB, axis angle to quat. which is exactly using these formulas, okay? But let's first show where these formulas come from. So if you have those built-in functions and you have the robotics toolbox to have those functions that I showed you here, you're good. If not, you can always write your own functions using these formulas. But in order to use a formula, you have to know how they came into existence, right? You have to show them. So where does this come from that if I know the angle and the axis of rotation in axis angle k and theta, I can relate it to a quaternion by saying the real part of it cosine is cosine of half angle. The imaginary vector of it is the axis of rotation k times sine of half angle. Where does this come from? Well, all that it comes from in this inverse orientation problem is, well, let's go ahead and compare the rotation matrices. So if you look here, this is the r of k and theta. This is what you multiply, pre-multiply by r to give you r rotated. This is also the rot q. This is the rotation for the quaternion, which again you multiply from the left by vector r to give you the rotated version, r prime. So both of these guys on the left and on the right, they do the same job. If they do the same job, then it means their entries should be equivalent of each other, okay? And how does that help me? Well, let's take a look. So it says Q naught is gonna be cosine of half angle. Where does that come from? Well, you know in here, if I add the diagonal elements, or basically calculate the trace of this, we have done it, if you remember. When we add all of these together, you are going to get kx squared plus ky squared plus kz squared times v theta, which is 1 minus cosine, plus 3 cosine. So the result of that, if you remember from the axis angle video, it is 1 plus 2 times cosine of theta. This is the result of the trace for that matrix. Now, what about this guy here? If I calculate the trace here, what do I get? So I'm going to add these guys together. Let's see what I will get. So if you'll see, there are 3 q naught squared. Every one of them is positive. So you are going to get 3 q naught squared. Here you have a positive q1, here you have a negative, here you have a negative, so you end up with a negative q1 squared. The same thing happens to q2, positive, negative, negative, so it's negative q2 squared, and also q3, positive, negative, negative, positive, so it is going to be negative q3 squared. Okay, so that is the trace, but now you can do a little bit of manipulation on that. Instead of this, you write it as, okay, what you do is you make this guy 4 q naught squared, but minus q naught squared, if you don't mind. Instead of 3, I write it as 4 minus 1. And then I write the rest of them. Now, this whole thing, all of these guys in negative, if you factor out the negative, it is going to be the norm of the q. And you know, norm of q is 1. So this is simply going to be 4q naught squared minus 1. And now guess what? This 4q naught squared minus 1 has to be the same as what? 1 plus 2 cosine of theta. Now, does that give me my first equation? Yes. How? So if I take this negative 1 to the other hand side, the right hand side, it becomes 4q naught squared is equal to 2 plus 2 cosine theta. Correct? This 1 plus 1 becomes 2. Divided by 4, it becomes q naught squared, which by the way, q naught is the same as eta. Eta squared is equal to 1 plus cosine of theta divided by 2. right? I simplified both sides by 4. And you know from trigs, this guy is cosine squared of half angle. So clearly from here, your eta is what? Cosine of half angle. And I guess this is exactly what you have over here, right? This is this guy. So the real part of a quaternion is equivalent to cosine of half angle in what? In axis angle, excuse me, representation. Good. So I guess I could prove to you, and hopefully you accept it from me, that that's how you get your first formula. Good. Now, what about the rest of it? So the rest of it says the rest of the q's, 1, 2, 3, which you can collectively call them zeta, they come from what? Multiplying the k unit vector by sine of half angle. Well, where does that come from? Well, let's take a look at that as well here. So let me clean this up. So where do we get that one from? So what we have here is, let's compare again if you want. So let's look at the entries. So zeta means q1, q2, q3, k means kx, ky, and kz, and sine of half angle. Where does that come from? So let's take a look. If we look at here, do you remember how we got k's back in axis angle? How do I get kx, ky, kz? If you remember back then, I subtracted the elements that were mirror image of each other with respect to the diagonal. So for example, I subtracted this one and this one because they both shared kx, ky, v theta. So when I subtracted, I got 2kz sine theta, right? So in this case, if I subtract these two, the result is what? 2kz times sine of theta, right? That's element 2, 1 minus 1, 2. Now let's do the same thing here. I subtract this one and this one. If I do that, let's subtract. If you see, they both share q1, q2, so that goes away. And the result is going to be 2q0, so it's going to be 4q0, q3. Yes? So 4q0, q3 should be the same as what? 2kz times sine of theta. Right? And what was q0 itself? It was cosine of half angle. So it becomes that, and if you simplify a 2 from both sides, you will get 2 times q0, and q0 was cosine of half angle, times q3 is equal to kz sine of theta. And what is sine of theta based on the cosine and sine of half angle? If you know, it is equal to 2 sine of half angle times cosine of half angle. And now if you simplify a cosine of half angle times 2 from both sides, you clearly can see that q3 is kz times sine of half angle. If you repeat the same thing by subtracting the other of diagonal elements, the mirror image of each other, you'll see that q2 will turn out to be ky times sine of half angle, and you'll see that q1 will turn out to be kx times sine of half angle. So if you combine these three together, you will see that q1, 2, 3, which is zeta, is equal to kx, ky, kz, which is k, times sine of half angle. And so you will get this formula. Okay, so very easy, you can relate your axis angle to what? To quaternion. So if I give you theta and k, you should be able to give me back zeta and eta, right? Or if I give you eta and zeta, you should give me back your theta and your k. So converting axis angle to quat and quaternion and vice versa is very easy through these two formulas, okay? And these two, as I said, you can use them with, these are what are used in the commands axis angle to quat and quat to axis angle, okay? So this is what used in that two formulas. Good. So these are clear now, hopefully. We used them earlier, but now you clearly see where they come from. Now, the other thing is, what about quaternion to rotation matrix, right? So I already told you how to go from quaternion to rotation matrix. So quat to rotation matrix is easy. What about backwards? If I give you a rotation matrix like this, and I ask you to give me the quaternions Q0 all the way to Q3, how would you do that? Okay, so how does this built-in MATLAB function work? Well, here it is using these formulas, especially the top row when Q0 is not 0. But where does it come from? Again, I guess that's not a big deal to show this, because last time, if you remember, I added the three diagonal elements together. I found the trace. And if you remember, when I calculated the trace for you, if you just remember from a minute ago, it was 4Q0 squared minus 1. So that thing is clearly equal to what? To the trace of matrix R. So if I take this 1 to the other side, divide by a 4 and take the square root, you will exactly get this formula. The square root of 4, 2 comes out of the square root. So this 2 is outside the square root. And you get a plus and minus, right? You get two answers for Q0. So here you have two solutions again. The solution is not unique. There are two solutions. One positive Q0, one negative Q0. Good? So the first formula is very clear. And again, the rest of the formulas are also very simple. Let me show you this one. So it says if you subtract element 3, 2, minus 2, 3, divide by 4Q0, that's what you should get for Q1. And again, that's extremely easy to show. All you need is to subtract element 3, 2, which is this one, minus element 2, 3, which is this one. If you subtract them, clearly the similar terms go away. And if you subtract, you will get 4Q0 Q1. This is equal to R32 minus R23. Right? So all you need is to divide both sides by a 4Q0 to get Q1. And similarly, by subtracting other off diagonals, you will get Q2 and Q3. So you see, the formulas are very easy to show. Good? So the top row formulas are not so hard to show. And they work perfectly well as long as this denominator 4Q0 is not 0. So you're not dividing by a 0. Okay, so they work perfectly fine. Now, what happens when this denominator Q0 is 0? Remember in previous cases when we had the Euler angle, when the mid angle became what? 0 or pi, you had singularity. You could not solve for all three of them uniquely. In axis angle, when the angle theta, the rotation angle, became 0 or pi, again you had singularity. So here you might suspect that, hey, when this real part of the quaternion Q0 becomes 0, again, I will get into trouble and I will get singularity. But the matter of fact, not really in this case. Even if Q0 is what? 0. How can you get the other Q's? In other words, can you have a quaternion like this? 0, okay, Q1, let me see, my pen writes again, Q1, Q2, and Q3. Can I have a quaternion like this? Yes, you can. And remember, this 0, which is your cosine of half element, what does that mean? Right? When this guy is 0, it means half of your angle has a cosine of 0. So this whole thing was 90 degrees, and it means your theta has to be what? It has to be 180 degrees. So when your angle is 180 degrees, half of it is 90, cosine of 90 is 0. Right? And remember, this was the case of singularity in x's angle, right? Theta of pi was singularity. Now let's take a look at this case. Is that going to cause a singularity? Well, if theta happens to be 180, or your quaternion is of this form, where q naught is 0, what's going to happen to your quaternion? So let's take a look at the quaternion. So what I will do in this quaternion, anytime I see a q naught, I set it to 0, right? So this goes away, here, 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 and here, right? So when that is the case, it means what happens to my quaternion? My rotation matrix, my rotation matrix will turn out to be what? Will turn out to be Q1 squared minus Q2 squared minus Q3 squared, and then Q2 minus 1 minus 3, the square term, and this should be Q3 squared minus 1 minus 2, I assume. Yes. Here is going to be 2Q1 to Q2, both of them. You will have 2Q1, Q3. And you should have 2Q2, Q3. Okay, so now can I find the rest of the q's when the q naught is 0? And the answer is yes, I can. In this case, I don't need the trace. Okay? In this case, I do not need the trace. All I need is to simply focus on the diagonal elements. That's all I care about here. Let's focus on these diagonal elements, see if they can give me Q1, 2, and 3. How? Well, if I look at this guy here, I can write it as 2Q1 squared minus Q1 squared minus Q2 squared minus Q3 squared. Yes? Now, how much is this guy here? If I also had a Q naught squared here, that would be the norm squared. But remember, Q naught is 0. So, of course, I can add a 0, no problem. So this whole thing should be what? Negative 1. So that element is simply what? 2Q1 squared minus 1. And that should be equal to element R11. There we go. What is Q1? Take 1 to the other side, divide by 2, take the square root. That's this formula. And you can do a similar trick to element 2, 2, and 3, 3, and show that Q2 and Q3 can come from those entries in the rotation matrix. And that means that although I had a case where in x's angle I had singularity, in this case I don't. In this case, theta of 180, which can be a potential for a singularity, does not lead to singularity, right? Even though that is 0, these guys, there is no reason for them to not be found, because you definitely have these diagonal numbers, and you can add them to 1 and not dividing them by 0, just dividing by 2 and then take a square root, right? And so clearly you're going to have 2 solutions for each, right? So we have one set of positives, one set of negatives, and the same thing here. With the positive Q naught, you have one set of solution. With negative Q naught, you have another set of solution. So there will be 2 sets of quaternions for each given rotation matrix, and there is no singularity. That's the reason quaternions are used as the stable or the reliable method of showing orientations. Because whenever you are calculating them, you will not go to any mathematical singularity. That's the advantage of this method. Although they are hard to understand, although you need to learn a little bit of algebra, how to form the rotation matrix and then use them, multiply them, add them if you need anything like that. But you clearly can see that it's worth it when you're not to worry about the singularity. Okay, so this is the unit quaternion. As I said, there are tons of MATLAB built-in functions that can convert your axis angle to quat to rotation matrix, can convert your Euler to quat. Now, there is nothing directly between Euler and quat. So if I want to show the 4 forms that I have shown you, what we have is the rotation matrix. What we have is the set of Euler angles. What we have is the axis angle. And what we have are the quaternions, unit quaternion. So these are the 4 different ways that we have seen to show the orientation. And which ways did we learn to go from one to the other? So for all of them, there was a rotation matrix. So for Euler angles, there was a rotation matrix. For axis angle, there was the Rodriguez formula. And for this one, there is the Hamilton rotation equation. So all of them can be converted to a rotation matrix. Now, these 2 guys can be converted to each other through these formulas I just showed you. This cosine of half angle and k times sine of half angle, that allows the conversion between axis angle and quaternion to be done very easily. Okay, but there is no direct simple conversion between Euler angles and axis angle and Euler angles and quaternion. Okay, there was no formula that we have seen in this slide number 4, in this slide number 2 and 3. Okay, Euler angles, you can directly relate them to rotation matrix. So how does this command work here? Like for example here, it says Euler to quat, right? So it means it goes from here to here. Well, it cannot directly. What it does, instead of that, it goes first from Euler to the rotation matrix. And since from rotation matrix, you can go also back to all of them. So not only you can go from Euler to rotation, you can go back from rotation to Euler, you can go back from rotation to k theta, and you can go back from rotation to quat, right? These are all of these formulas are the inverse orientation problems I gave you a formula for, right? So this is the inverse for Euler. This is the inverse for axis angle, and this is the inverse for what? For the quaternion. So I also know how to go back from rotation matrix. So if I want to go from Euler to quat, what do? I go from Euler to rotation, and then from rotation, I go to quat. So instead of this green path, I go through these 2 black paths. And the same thing for axis angle, right? Yes? So that's how MATLAB doing it. It is combining. But in general, this is what I really learn through these formulas. These are the connections. These are the formulas that I have learned. And then, as I said, since I have these two-way path. I can go from any point to any point of this kind of graph. So hopefully you have seen and you have learned the 4 different methods of rotation representation. You have seen relevant MATLAB commands. You have seen where the formulas are coming from. And we try to soon, after we are done with the slide number 6, which is bringing in translation and adding it to rotation through a homogeneous transformation, then we are going to see how we can use all of this info to represent the position and orientation of any part in the robot, including the end of it, which we call end effector, with respect to any specific sensor, any specific system, inertial system, and so on. Okay, so this is extremely fundamental later when we go and solve forward and inverse kinematics problems in the robot. So thank you so much for your attention, and I will see you in the next lecture.